Hello dear students, welcome you all. In this lecture, I am going to discuss about the Maxwell-Boltzmann distribution law, right? Maxwell's Boltzmann distribution law, right? We are going to drive the Maxwell-Boltzmann distribution law here, right? For driving this Maxwell-Boltzmann distribution law, to enter in the discussion of Maxwell-Boltzmann statistics, we have three wings of statistics. One is Maxwell-Boltzmann, that is classical, clear, and others two are Bose-Einstein and Fermi-Dirac. These two statistics are quantum statistics, right? When we enter into the different problems of classical statistics, uh, we have to first drive a distribution law for the distribution of classical particles, right? Here, classical particles means those particles which are distinguishable, right? In classical word, we can differentiate between two particles, right? Another important feature of the classical physics is that there is no restriction on the number of particles entering in the any number of compartments, right? These two parameters are very important in classical statistics, right? So here in this article, we will drive this distribution law, right? So to do so, let's assume we have undistinguishable particles, right? Particles, right? Obviously, in classical physics, these particles are gas molecules, right? Best example of classical particles are gas molecules, right? So here, what we have to do, we have contained these gas molecules inside a container, right? This is the container, or enclosure of volume B, right? This is the container or enclosure of volume B, right? In which these N gas molecules are present, right? Which are obviously distinguishable particles, right? Uh, here we assume that when these gas molecules are present inside this container, they are continuously undergoing collision with each other as well as collision with the walls of a container, right? It means their energy and momentum are changing continuously, right? When I talk about the different particles, right? These are the different particles, gas molecules inside the container, right? So these gas molecules are continuously colliding with each other as well as with the walls of container, right? And due to it, there is a continuous change in the energy of these gas molecules, right? But here we assume that the total energy of these gas molecule is constant, right? There is no loss of energy. It means this entire system is a isolated system, right? The total energy E of these gas molecules is E is equal to constant, right? One more thing is total number of gas molecule N, they are also constant. Clear? There is no escape of gas molecule from this enclosure, right? Now let's look at this problem, right? If we look at the different gas molecules inside this enclosure, obviously some gas molecules have some range of energy, other will has other range of energy. I can say if I consider that the total energy available in this given volume is I mean 100 joule, right? Then some molecule will be having the energy in the range of 0 to 5 joule, some will have 0 to 10 joule, other may have up to 15 joule, so on. So we will have different range of energies, right, in which these gas molecule will be present, right, at any time. Right. So I can say that I can divide this given volume into different compartments, right? Energy compartments. Clear? Each compartment corresponds to the different energy, right? Right. This is compartment number 1, 2, and 3, so on. That this is the kth compartment. Clear? Now, here we have different compartments. Let this compartment correspond to the energy range E1. Similarly, this corresponds to energy range E2. This corresponds to energy range E3. Similarly, this corresponds to energy range EK. Right. So what we did here, we divided the given volume into different energy intervals, and this problem now becomes analogous to the distribution of indistinguishable particle in k compartments of unequal size, which are further divided into cells. So for that, what I do, I further divided these compartments, right, into small cells, right? So in that way, now all the energy cells becomes, these small cells becomes equal, but the different compartment has a different number of cells. What I'm trying to say that this problem is now analogous to the problem of distribution of n distinguishable particle in k compartments of unequal size, and these k compartments are further divided into cells, right? Here the difference is these compartments represent different energy levels, right? And these small cells represent the small energy levels, which are having equal energy for all the compartments, right? This, I mean, this compartment, this cell, all are of same energy, right? So now, this problem, as I told you, it is analogous to this. So, in this case, now let the number of particle in the first compartment is N1. Similarly, in the second goes N2, N3, and this goes Nk. The number of cells in this is Z1. This has Z2. This has Z3. So on, all these things are exactly analogous to the problem that I told you, right? Distribution of n distribution particle in a k compartment, right? So we know in this case, right, and in that case, as the total number of meaningful arrangements, that is thermodynamic probability, we have derived this expression for the macro state n1, n2, so on nk, right? That was what? That was n factorial into multiplication of I go from 1 to k. It was, sorry, here, then zi power ni upon, right, ni factorial. So right, so this was the expression that we have derived in the earlier topic. Clear? The topic of the distribution of n particle in k compartment of unequal size. Now here the problem is exactly analogous. Here, in place of particles, we are considering the gas molecules contained inside a container, right? And in place of area, we are saying that we have a total energy E. Clear? That energy is divided into small compartments or intervals of energy E1, E2, E3, EK. These energy intervals are further divided into small cells of energy, right? So this is the analog between the two situations, right? Now let's solve this equation. This is equation number 1. Okay? Taking log on both the sides, natural log w is equal to log of e n factorial, right? Plus summation I go from 1 to k ni log of e gi minus summation of I go from 1 to k log of e n I factorial. Clear? So what I did, I simply took log on the sides. Now here I will apply the Stirling formula in these two terms of this equation. Why? Because here is a n factorial, right? So when I will apply the Stirling formula, it will become n log of n minus n plus summation of ni log of gi minus ni summation of log of ni, right, minus n log n, right, minus ni. Clear? But again it is a summation here. Let's write it this way, because summation is common, summation of ni. Clear? So when I will take summation of ni, what it will become? It will become n, because summation of ni means n1 plus n2, so it is equal to n. So here it will become n. Clear? So when you will have n here, this will get cancelled. Right. Here it was negative, but it will become positive. How? Because here it is negative. So when you will take a log of n factorial, n log n minus n, so it will become plus. I have wrote here minus, it was wrong, sorry for it. So plus this got cancelled, right? So now we are left with the n log of n plus summation of ni log of gi. Now I am not taking e here. It is understood, minus summation of ni, right, log of ni. One mistake that I did, it should be here, right, because both are here. It is also summation, here it is also summation. So now I corrected it in this step. Now I have this, so log of w, right. Now differentiating both the sides, taking d. Clear? Log of w, but remembering that n and gi are fixed, constant, right? So it will become, this term will become 0. Differentiation of this term will become 0. Here it will become summation of ni means dni log of gi. It is a constant, minus, right? Now bracket, because we have two variables now, dni, right, log of summation was also there, log of ni, clear, plus dni, it is plus now ni into 1 upon ni into, right, dni. So ni as it is, differentiation of it 1 upon ni into differentiation of it, right? So it got cancelled, right? So you will get here one mistake that I have done is here again it will be summation symbol also. Otherwise we can take this summation outside, in that case it will be the same thing. So now it will become summation of dni log of gi minus, right, summation of dni log of ni, right, minus summation of dni. Now this summation of dni, we know summation of ni is equal to constant, right? It is fixed. I have told you in the beginning that n is constant, summation of ni means n, so dni is equal to 0, right? So now I am left with the d log of w is equal to what? Summation of dni log of gi, clear, minus summation of dni log of ni, right? I can say even log of summation log of gi upon ni, right, into dni. I can write it in this way, d log of w. Now we know for the most probable state, right, equilibrium state, w is equal to maximum. W is equal to w maximum. So D of this stable value should be equal to 0. It means this is equal to 0, right? So it becomes now, right. Now we have this equation. Let this is equation number. Let we have an equation. Yes, it is equation number 2. Clear? This is equation number 2. Clear? I go from 1 to k. Now we are applying two conditions. The first condition was E is equal to constant. I have stated in the beginning. So E is equal to constant means summation of EI Ni. This is actually the sum of energy of all the gas molecule. It is equal to constant. Clear? Now, when I take D of this equation, then it becomes summation of EI dni. It should be equal to 0. Right? Similarly, if I take n, that is total number of constants, summation of ni is equal to constant. Clear? Then again summation of dni, that should be equal to 0, that I told you here. Right? Now what we will do, I will let this is equation number 3 and this is equation number 4. Clear? I will multiply this equation with alpha and this with the beta. Clear? And then I will subtract these equations from this equation number 2. Clear? I can do it. So in that case, it will become summation of log of gi upon ni into dni, right, minus alpha summation of dni minus beta summation of ei dni is equal to 0. So then I can take dni common in all the terms, right? So it will give me summation of log of gi upon ni minus alpha minus beta e I whole term, right, like this, into dni is equal to 0. But we know since these variations d and I are independent of each other, so this summation cannot be equal to 0. It means the term inside the bracket, that should be equal to 0. Log of gi upon ni minus alpha minus beta ei, that should be equal to 0. So I can take this toward this side, so it will become alpha plus beta. Clear? So when you will simplify it in next two steps, you will simply get ni upon gi is equal to, first of all you will take the exponential, then it will become gi upon ni is equal to e raised to power alpha plus beta of e I. Clear? Then you will take it, you will make this denominator, it will make denominator, you will take 1 upon this of this equation, invert this equation, then it will get ni upon gi is equal to 1 upon e raised to power alpha plus beta ei, right? Or you can write ni is equal to gi upon e raised to power alpha plus beta ei. So this is the required result distribution law for Maxwell-Boltzmann statistics. This figure, this is sometimes also called as a occupation index, right? It tells us about the number of particles per unit number of cells in the given energy interval, right, in terms of alpha and beta, right? Similarly, you can use this equation also. So this equation is linked with the ratio of the number of particles to the number of cells, right, in terms of the energy value, right? So this result is very, very important, and it is the beginning for all the applications of Maxwell-Boltzmann statistics, right? So we have derived this law by making an analogy of this distribution to the distribution of n distributable particle in a k compartment. right? So in the coming articles, we will apply this, right? So thank you very much.